But let's start with the warm-up question. The first one says, what wave behavior is shown here? And then the second one says, Mars orbits the sun at 228 million kilometers. How long in minutes does it take sunlight to reach Mars? So let's start with the wave behavior one. You guys had an assignment on Friday where you were looking at wave behaviors again. We've already talked about them before with mechanical waves, but we talked about, or you guys looked at the same behaviors with light. Which one would be represented here by this pencil and this glass of water?
Reflection.
Not reflection, refraction, yeah. Okay, refraction. You have the wave changing medium, going from air into glass and water actually. But when that happens, the speed of the light changes, and when the speed changes, it also can cause the wave to bend. And we'll look at it again a little bit more today. But number one is refraction.
Oh, you're talking about
the pencil one.
Pencil.
Yeah. Number two, Mars orbits the sun at 228 million kilometers. How long in minutes does it take sunlight to reach Mars? We did a problem like this in our notes last week. And we talked about how the information that we're given here, we don't have time in our wave equation. We know that the speed of light, or the velocity of any wave, is equal to its frequency times its wavelength, but those aren't the variables they gave us. So we're going to go all the way back to unit 1, and we're going to use that constant velocity equation, because that velocity is still equal to distance over time. So the speed of light would be equal to the distance traveled divided by the time that it takes. The only problem is that we have our distance here in kilometers and we need it in meters. So I've already done that conversion up here. That 228 million kilometers is equal to 2.28 times 10 to the 11th meters. My speed of light is a constant 3 times 10 to the 8th meters per second. And so if I want to solve for time, we're just going to substitute into that equation that speed of light equals distance over time. Okay, so here's my speed of light, here's my distance traveled, here's my time. I'm trying to solve for t. Again, you cannot solve for the variable when it's in the denominator, so we're going to multiply both sides by t, which brings it to the top. And now to isolate that variable, you're going to divide both sides by 3 times 10 to the 8th. So this is what goes in your calculator. 2.28 times 10 to the 11th divided by 3.0 times 10 to the 8th. Again, I would recommend that you practice typing this into whatever calculator you plan to use for the test, so that you're making sure that you're not having issues with entering that information in there. So if you haven't tried it yet, please do so. When you divide that, you get 760 seconds, which is not our answer because the question asks how many minutes. Okay, but the unit you're going to get here is seconds because the speed is in meters per second. So when those meters cancel, all you have left are seconds. So 760 seconds, if I want that in minutes, I just need to divide by 60, and I get 12.67 minutes. So just a little bit longer than it takes light to reach Earth. By the way, does anybody know how long it takes light to reach Earth?
8 minutes.
Yeah, about 8 minutes. I think it's like 8 minutes, 20 seconds, but yeah. Okay, so anyway, I was just curious. But yeah, a little bit longer because Mars is a little bit further away. But anyway, go ahead and make sure that you have entered the answers to your warm-up question.
Interference?
No.
Because there's
It would be transmission and refraction for the first one. All right, again, make sure you have those answers in there, and then we're going to get into some notes today and talk about one of the more complicated things in terms of concepts that we talk about in here. Magnetism was up there. This is the other thing. Not this, but we're going to be talking about wave-particle duality today. But we do need to first talk about wave behaviors of light. So this is what you were looking at in the simulation that you did, or hopefully did, on Friday. If you didn't do that, you need to make sure that you get it taken care of. But we know that light behaves as a wave, just like sound waves and any other type of mechanical waves. Light waves can undergo reflection, diffraction, transmission, and refraction, the same wave behaviors we've already talked about. And so a lot of this is going to sound really familiar as we talk about it. I will say this part's a little bit different, or side note. We talked previously about how light really doesn't diffract at least not visible light, very well, but that's because if you recall when we talked about diffraction in our last unit, we said that the diffraction was only noticeable when the opening was smaller than the wavelength of the wave, and light waves have very tiny wavelengths. So in order for you to see diffraction of visible light, which we will talk about a little bit later, you have to have very, very tiny obstacles or openings in order to actually see that diffraction. But it is something that light is capable of doing. So again, we have these wave behaviors of light. So we know that light behaves like a wave, like every other wave. So we know that it reflects off surfaces like glass, your mirror in the morning, that's probably what you did when you were getting ready, ponds, surfaces of water, every surface. If you can see that surface, it's because light is reflecting off of it, like your desk in front of you, the walls. Anything that you can see is because that light reflects and then goes into your eye. Reflection is evidence of wave behavior, but particles also reflect. If I throw a ball at the wall, it's also going to bounce back. Okay, and so it's not definitive proof that light is a wave. But I'm going to show you this video about reflection and how we view the things around us. It's a video about this material called Vantablack that doesn't really reflect very much light at all, which is going to make it look kind of weird, if I can get it to play. And then we'll talk more about wave behavior. It's over here.
Here's an interesting clip, and what we've done, we've overexposed it massively and then dropped the lighting back so you can see how the shape suddenly appears out of nowhere.
A high-tech company by the name of Surrey Nanosystems claims to have invented the blackest black you have ever seen, which goes by the name of Vantablack. Vantablack is the definition of darkness. It's a material that absorbs 99.965% of ultraviolet, visible, and infrared light. This super black coating holds the Guinness World Record as the darkest man-made substance. To give you an idea of what that actually looks like, Vantablack has been described as the closest thing to a black hole we'll ever see. Vantablack is so dark that the human eye can't discern its shape and dimension, which means if you were to cover a round object and pass it in front of another object coated in Vantablack, the round object will disappear and both objects will appear completely flat. The material is able to get so dark thanks to tiny carbon nanotubes that are roughly 3,500 times smaller than a human hair. A surface area of 1 centimetre squared would contain around 1,000 million nanotubes, and when light hits the tubes, it's absorbed and cannot escape. The name Vantablack is an acronym for Vertically Aligned Nanotube Array Black, and Vantablack is not a colour, but a material. It's made of a forest of tiny hollow nanocarbon tubes, each the width of a single atom. Because it's not a pigment or paint, you can't just buy a tin of it like paint. The nanotubes that make up Vantablack must be grown in the Surrey Nanosystems lab using a complicated and patented process involving several machines, a few layers of different substances, and some extreme heat. From start to finish, applying Vantablack to an object can take up to 2 days. If you see it on a flat surface on its own, with no other black material to reference it against, it just looks like a black velvet surface, until you shine a torch on it and no light is reflected back. And when other black surfaces sit side by side with it, they look grey in comparison. Vantablack is not very robust. It may be able to withstand extreme cold or heat, but because it's made of delicate carbon nanotubes that are more than 99% empty space, it can't be touched without damaging the effect of the coating. So don't expect to see any stealth bombers covered in the coating. Vantablack is designed to reduce unwanted stray light and is highly desirable in space applications, but can be used in a wide range of other applications, including high-performance infrared cameras, sensors, scientific instruments, satellite-borne calibration sources, star trackers, and telescopes, and can even provide a unique aesthetic effect in certain high-end luxury products like watches. Oh, and to all you YouTubers out there, if you're thinking of buying some Vantablack for videos, don't bother. It's not sold to private individuals as the coating is subject to UK export controls. Anyway, that's the end of this video. Thanks for watching and we'll see you next time. Bye-bye.
So like I said, we see these objects around us because of the way that they reflect light. That's just an interesting material because it really doesn't reflect very much light at all, and it makes it impossible to really discern the shapes of the objects that are passing in front of it. But again, light does reflect, and some objects produce their own light. So these are just two vocabulary terms that you're going to want to write down in your notes: luminous and illuminated. A luminous object is one that produces its own light. So like the light bulbs in the room, or the sun, or fire, anything that produces its own light source is called a luminous object. An illuminated object, sometimes called a non-luminous object, is one that reflects light. So it's something that you see because you have light coming from that to your eye, but the object itself isn't producing the light. The moon reflects the sun's light. That's why we see it in the sky at night. It is a good example of an illuminated object. It does not make its own light. The desk you're writing on, a mirror, surface of a lake, basically anything else that you can see that doesn't make its own light is going to be an illuminated or non-luminous object. Again, with our luminous objects, we talked about this already in our notes last week, but the color that you see is determined by the element and its electrons, and we looked at those electrons becoming excited and then falling back down to ground state and releasing very specific colors. And so that's how you get color from a luminous object. But an illuminated object, what color you see for those objects is determined by what light is reflected. So like a red object reflects red wavelengths, for example, and that's why it appears red to us, because the red would come bounce off of the object, and then that's the light that goes to our eyes. So again, just two terms that you want to write down, maybe some examples of them, and if you wanted to write down about how the color of the object is, how you perceive that color, then here's what you would want to add for that. By the way, if I go too fast for you, this is slide 31. You're welcome to follow along on your own. Okay, so we know that light reflects. One of the other wave behaviors we talked about is refraction. Light can pass through materials that are transparent, objects with a low optical density. That's the way that we describe that transparency or degrees of transparency. However, when light travels into these materials from the air, refraction is noticeable. Light travels slower in denser materials like water. So the light will slow down whenever it goes from the air into water, which is what causes this apparent bending or even broken look of the pencil from the warm-up, or like the straw in your water glass. I'm sure y'all noticed it before, that it does look like it is bent. It is because the speed of those light waves is changing. And remember, if they approach a new medium at an angle, okay, then it causes the bending because the front part of the wave slows down first before the back part of the wave. Okay, so here's an example explaining how that bending occurs. The bottom part of the wave reaches the glass first and slows down. This causes the wave to bend. When discussing which way a wave bends, we describe whether it bends toward or away from the normal. So the normal is this red dashed line that I just added to the image. It's an imaginary perpendicular line to where the ray hits the boundary. But in this case, we would say that it bent toward the normal because it got closer to this line than it was originally. And so you do need to be able to describe which way something's going to bend, either away from or toward the normal. So here are the rules. You again may want to write down in your notes. But if when light changes medium, it refracts. Again, here's an example going from air through glass of some kind and then back into the air. So you can see that there is bending whenever it goes into the glass because it's traveling at a different speed. You can even tell that it's moving slower if you follow this little arrowhead. But again, it will bend toward the normal if it slows down. So we know that it slows down in glass, and you can tell that this angle, it's labeled as a B right here, is smaller than this angle A. And again, that's because it got closer to the normal because it slowed down. That's the rule. It bends toward the normal if it slows down. Example, entering a more dense medium like glass. It bends away from the normal if it speeds up. So when it leaves the glass and goes back into the air, again, it bends away from this imaginary normal line, giving us a larger angle here than we had in the glass. Okay, so entering a less dense medium, for example, would cause it to bend away from the normal. So you do want to remember those rules. I would write them down. If you want to draw a picture too, that might help. but you need to know which way it's going to bend. You might see a question and it may say, which of these is a more dense material? Okay, or if this shows light going between two mediums, glass and air, which one's the air? Okay, so you do need to be able to use these rules and apply them to different situations so that you can answer those types of questions. Okay, so again, we know that refraction is a wave behavior, so we know that that's yet another piece of evidence that could show that light is a wave. I've already told you it's a wave, but whenever they were originally investigating the nature of it, of course, there were a lot of questions they were asking. The problem is that particles can also refract, and they can also reflect. Okay, so there was not, again, definitive evidence that it was a wave until this is one of the first things that actually shows just pure wave behavior. It's called polarization. So we've looked at this, or talked about this before because I showed you an animation of those electromagnetic waves, but light oscillates in multiple planes. It's these oscillations of electric and magnetic fields, but it's not just up and down or just left and right, it's both, and even some at diagonals too. This light can be polarized by passing it through a polarization filter or grating that forces it to vibrate in only one plane. So if you have polarized lenses on your glasses, okay, if you watch this animation here, there's a lens in front of a computer screen, and you can see that when they rotate it, it blocks out the light entirely, and then you rotate it back and you can see what's on the screen again. It's because of these very small slits in this polarization filter or grating that blocks certain types of light that are vibrating in certain directions. Okay, so the polarization film itself is a fine filter that has lattices arranged in one specific direction. So although you can't see them, there might be tiny slits in that film that are all vertical, or maybe they're all horizontal. Okay, and by doing that, they only allow certain parts of the light wave through. So this is what I'm talking about. You can see this animation here shows unpolarized light, so just the raw light coming from the light source in the room or coming from the sun, and you pass it through one of these polarization films. And this one here on the left, it shows that the direction of the slits in the grating are all vertical, so only the vertical part of the wave passes through. It blocks everything else. This one over here on the right, you can see that it shows horizontal polarization, where only the horizontal waves are allowed through and everything else gets blocked out. So these polarization films specify the geometric plane or direction of the oscillations of the light waves. They basically filter out everything that isn't able to go through those openings. Okay, so they force light to only vibrate in one plane, and again, this is not something that a particle would do, it's only something that a wave would do, and so this is evidence of the wave nature of light. Okay, so this was one of the things that helped to prove, hey, light is definitely a wave because it can do this. Okay, so again, the types of questions you might see would be something like this. Draw and describe the result of shining unpolarized light through two polarization filters when one of them has a vertical transmission axis and one of them is horizontal. Of course, the first one that it passes through, it's going to block out the horizontal rays, and then the vertical rays will continue forward, but when they approach this second film, they can't go through it. So if you did do this, no light would pass through, which is what was happening with those sunglasses. When they were rotating them in front of the screen, they were lining them up so that one of them was vertical and one of them was horizontal, because the screens of your devices can be like this as well. I know one of my older phones that I had at one point, whenever I was looking at the phone with my sunglasses on, it was black. Like I had to rotate the phone sideways or take my sunglasses off because it was doing this. So again, this would allow no light to pass through. The first filter would eliminate the horizontal waves, and the second one would eliminate the vertical waves. All right, so another of our wave behaviors is interference. Light can interfere under certain circumstances. One of the best examples of interference is demonstrated by the light reflected from a soap bubble. You get these swirls of color on a bubble. I'm sure you've noticed it before. There's one that's with the image down here that's showing kind of the same thing, or like oil on the surface of water, kind of same idea. but it reflects a variety of beautiful colors when illuminated by natural or artificial light sources. These different colors that we see come from the simultaneous reflection of light from both the inside and outside surfaces of the bubble, and those reflections then interfere with each other, and you get these kind of cool swirling color patterns. Okay, so again, interference, yet another wave behavior. Diffraction. Light can diffract, I mentioned that earlier, but only if you have tiny openings that are micrometers thick. Maybe you've heard of Thomas Young's double slit experiment. If not, this is showing kind of what he observed with that. But basically what he did was he took this light and he shined it at a piece of foil that had two very tiny slits in it, just like this has two very tiny openings in it. And he saw on the screen on the other side, you would expect if there were two openings to see two bands of light, but instead he saw multiple bands of light. They were brighter toward the center and then got more dim as they went out, like this right here. And this was the result of the diffraction pattern that you see right here. We saw this with water waves as well, but light can do it also if you shine it through a small enough obstacle or opening. Okay, so again, diffraction, yet another wave behavior. So this is kind of what he was doing, these two slits, shining the light through it. You would expect two bands of light, okay, but that's only if it's a particle. Instead, he got multiple bands of light like this. Okay, so again, evidence of wave nature of light. The interference pattern produced bands of bright light, so this is what was observed on the other side, or something like that. Okay, so explain how diffraction can aid you in receiving good radio reception. Okay, I'm sure you're aware of this, but you probably don't have a direct line of sight to a radio tower. Okay, so those waves are able to make it from the tower to you around buildings, around trees, around all of these obstacles because of diffraction. They can bend around things, okay, like buildings or trees, and fan out or diffract when doing so. And this allows them to transmit signals to you even if you don't have a direct line of sight to the radio tower. I know most of you probably don't listen to the radio. You're probably streaming everything, but okay, that is important for that radio reception, that diffraction. Okay, so for a long time, it was generally believed that light was a wave. Like sound and water, it exhibits many wave behaviors. We just looked at these. Reflection, refraction, diffraction, interference, as well as other behaviors that are evidence of light's or of the light's wave nature, like polarization. Okay, so all the stuff we just talked about could be used as evidence to show that light is a wave, and it is and was used as evidence to show that light was a wave. However, in 1887, there was an experiment done with something called the photoelectric effect that showed light behaving in a way that could not be explained by a wave model. Okay, so the prevailing theory at the time was, hey, light's a wave, and then this experiment comes along, and now it's not a wave anymore. Okay, so I'm going to show you this video clip because I think it does a pretty good job of trying to explain something that's kind of complicated, so I'm going to ask you to give it your attention. It does have some fun sound effects, so all the photons and electrons make their own little noises. But go ahead and watch this, and then we'll talk about it.
In 1905, Albert Einstein made what seemed at the time to be a preposterous claim. Light, he said, behaves as both a particle and a wave. The insight won Einstein the Nobel Prize. So far, several experiments have confirmed that light is indeed a wave and a particle, but not exactly. The problem is that in such experiments, light behaves either as a particle or as a wave. No one has ever found a way to see it do both at the same time. Now, scientists at EPFL have designed an experiment that makes use of the way electrons interact with light to take a photograph of its dual nature. First, the researchers shot a pulse of light onto a tiny metallic wire, basically trapping it there as a standing wave, a wave that doesn't change position over time. But remember, because of the wave-particle duality of light, the standing wave of light is also made up of particles, the photons. Now here's a question. You need light to take photos, right? But how do you take a photo of light itself? The EPFL researchers figured out a clever way to do it. They shot a stream of electrons right past the wire holding the trapped light, so close that the light and the electrons were forced to interact. Because light is made up of photons, the electrons would hit them and either slow down or speed up. This change in speed can be measured as an exchange of energy packets, or quanta, between the particles. Then, using a specialized microscope that can see electrons, well, this is really what it looks like, the researchers were able to see where this exchange of energy happens along the wire. All that was left now was to take a photo. Et voila, the first ever snapshot of the dual nature of light.
So again, it's talking about some stuff that we've already kind of mentioned, quanta of light, stuff like that. We talked about last week a little bit. But again, here's the thing. Light is a wave, but it is also a particle at the same time. And yes, that is a weird thing to say or to think, but it is what we have evidence for and what is the prevailing scientific theory right now. So again, light behaves as both. It exhibits wave behaviors, but it also exhibits behaviors that cannot be explained by the behavior of waves, and this is how we got this wave-particle duality model. Okay, so here's kind of an analogy to hopefully try to make a little bit more sense. It says, suppose you have a chunk of gold and you cut it into smaller and smaller pieces. The smallest possible piece contains just one atom of gold because atoms are the building blocks of matter. If light is waves, then one can always reduce the amount of light by making the waves weaker. While if light is particles, there's a minimum amount you can have, like a single particle of light, just like matter. Okay, if you can only have an atom of gold, then you could only have a single particle of light. But if it's a wave, you could change it by any amount, making it weaker and weaker and weaker without there being a minimum. Okay, Einstein again found the answer. Light is both. Sometimes it behaves like a wave and other times it behaves like a particle. Okay, so that photoelectric effect experiment is the one that really showed that particle nature. So I'm going to explain what they kind of did there. So in the late 1800s and early 1900s, scientists were studying the nature of light. They did an experiment where they found that when light was directed at a metal plate, that they could cause electrons to be ejected from a metal and a current to flow if they hooked up wiring in an ammeter. So they had this light shined at this metal surface, and these electrons basically got kicked out of the surface. Okay, and they if they hooked it up to wiring, they could actually have those electrons traveling through a circuit of sorts where they could read or measure the current flow of those charges. So according to wave theory, they propose that if light is too low intensity, so if it's dim, okay, that the surface has to be exposed for a long time before emitting electrons and the energy would build up. So basically, if we keep adding energy to it, it should eventually have enough energy to escape, kind of like boiling water or something like that. Okay, if you add enough heat to it, it should eventually at some point have enough energy to escape. But that's not what happened. Okay, so this is what they thought was going to happen because they thought light was a wave, but that is not what happened whenever they did the actual experiment. Okay, so what happened instead is that there was no time required to build the energy up. The electrons were emitted immediately without any time lag, so long as the frequency of the light was high enough. So it wasn't the amplitude, it was the frequency. Okay, that was enough, causing them to have enough energy to escape. So this is how we came up with that relationship as well, because we talked about the fact that with mechanical waves, it was the amplitude that determines the energy, but with light waves, electromagnetic waves, it's the frequency. Okay, and so low frequency light, even if it had a really high amplitude, never emitted electrons. So again, this is kind of what they saw. They had these light frequencies that were too low, like red light. No electrons were ejected, even if they shined the light on it for a long time, even if they shined really bright light. If it was red, it didn't matter. But as you got toward the other end of the visible spectrum, the colors of the rainbow closer to violet, those moderate frequencies and especially those high frequencies, you did have electrons that were ejected. And with those medium frequencies, those electrons were moving kind of slow, low velocity. As you increase the frequency to like the blue or violets, those electrons got faster. And so they recognized that the energy of the electrons was related to the frequency of the light that was shining on the plates. Okay, and this occurred no matter what the brightness was, so it didn't matter what the amplitude was, it only mattered what the frequency was. Okay, so no matter how bright it was, if the light frequency was too low, no electrons were ever ejected, but if the frequency was above some minimum threshold, and that gave those electrons enough energy to escape. And the brighter light, more amplitude, caused more electrons to be ejected, but the energy of those did not change. Okay, so the energy was only determined by frequency. Only frequency affects kinetic energy. That was one of the conclusions that was drawn from the photoelectric effect as well. Okay, so if light were just a wave, it should be possible to increase the intensity of the light or wait for a period of time until the continuous addition and absorption of energy is sufficient to cause the material to leave electrons. Just like we should be able to add heat to water to boil it. That did not happen. The photoelectric effect proves that energy is quantized, that energy arrives in packets with very specific energy or quanta, and that these particle packets are called photons. Okay, just like they showed in the video with the electrons interacting with them, and they had these particles. Guys, we've talked about photons or quantized packets of energy before when we did this. We talked about this last week. Okay, that you have these very specific, unique energy changes that occur when these electrons fall from excited state back down to ground state, and they give off very specific, distinct colors of light. They're like rungs on a ladder. You can only go up to a rung. You can't go in between. There are very specific amounts and particles of light that are given off because of that. Okay, so the particle model of light is further supported by observations of atomic emission spectra. Very specific quanta of energy correspond to unique frequencies or colors of light that are seen when atoms are excited, and we had these kind of fingerprints, if you will, for these different elements. All right, so kind of to summarize, you might want to draw this chart on your paper, but we've talked about a lot of behaviors that waves have and that particles have. So reflection is something that you would see with both. Okay, a wave can bounce off of a wall, so could a particle. If I throw a ball at a wall, it will bounce back. We have reflection. Okay, refraction, again, both can do that. If you, and I don't know if y'all saw the animation, I should have pointed it out when we were on that slide, but for refraction, I also showed not just the light wave making the pencil look bent, but a bullet being fired through like a fish tank. You definitely have a change in velocity, and that bullet will bend as well. So particles can also show refraction. Interference, though, is really just a wave behavior, and so is diffraction. Okay, particles don't bend around obstacles. Particles don't interfere with each other in the same way that light waves can, where they can add together or cancel each other out. Okay, polarization was also just evidence of wave nature, but the photoelectric effect was only evidence of that particle nature, and those emission spectra show the same thing. Okay, so again, we have evidence that light behaves as a wave, and we have evidence that light behaves as a particle, and the truth is that it behaves as both at the same time. Okay, so that's the duality of light, or wave-particle duality. You'll hear that terminology used to describe it. Any questions about that? Again, guys, if I go too fast, this is slide 54. You're welcome to open it up on your own screen to finish copying it down. Okay, so if you have any missing assignments for this unit, that's all I'm going to ask you to work on for the rest of this period. If you didn't do the assignment Friday, for example, the other thing that I'm going to ask you to look at if you haven't opened it up yet is the video outline that you can find in My Open Math for the video RA project. Hopefully you have signed up for an RA topic. If you haven't done that yet, you need to do that first. But you can go in there with your group. And the video outline is mostly a planning document for you guys to have discussions. If you haven't looked at it yet, you'll see it whenever you open it. For you to have discussions with your group in order to kind of plan out, you know, who's going to bring what materials, where you're going to film, things like that, what type of video you want to do. That outline is due this Friday, so you don't really have specific class time dedicated to it. It's just the end of the period, like today. You'll have another day later this week. You do have a quiz over this unit on Friday. Your unit summary is also due Friday, and you do have a TEKS test on Thursday of this week.
Are we going to study for the TEKS test?
Um,
or are we just going in?
Well, I'm planning to give you a review for it on Wednesday, but I mean, you can study with everything that we've done this semester. It's only over this semester. All right, guys, so again, go ahead and either take a look at what missing assignments you have, or open up that video outline and get to work. If you have questions, please let me know.